Okay, so welcome to topic 4, review number 2. So we had the first one on Tuesday, and now we have this one. I am the only one running this one, so just me. My email's down there. We're actually going to start by going through questions, the clicker questions we didn't get to in class. So we're going to start by going through those, and then we'll go through the PowerPoint, which is some more exam-like questions. So we'll start. Sorry, there's like a lot happening on the top of my screen. Okay, can everyone see the clicker questions? Yes, no, maybe so. Yes, okay, thank you. So this is the one that we left off on, or not the one we left off on, but here's the next question. I think there's only 2 or 3. So if you want to put your answers in the chat, that'd be awesome. So this one is just which of the following are examples of non-coding RNAs? So it's numeric, so just pretend it's like an iClicker question, just submit it in the chat. You can send it to me individually if you're not confident. You don't want anyone else to see. If you have no idea, you can say no idea. This is a judgment-free zone. Okay, I got 1 person to direct message me. Can I get 1 or 2 more of you just so that I know that I'm not rushing? If you have no idea, can you just like direct message me no idea? I want to give everyone enough time to be doing these, but okay, you got some different answers here. This is a good one then. Okay. Okay, so I got a few different answers. Thank you for the person that said no idea. I appreciate it because then I know that I'm not going too fast. Okay, so the correct answer here is 2, 3, 4, and 5. And then we can have a little bit of a discussion about 6. So number 1 is not correct. mRNA is a coding RNA. That is our coding RNA, messenger RNA. Non-coding means that we don't use it to make a protein. So our RNA is ribosomal RNA. So that is the enzymatic portion of the ribosome. And if you remember, the ribosome is what reads the mRNA to make the protein to do translation. So our RNA is a non-coding RNA. tRNA is the RNA that brings in the amino acid to the ribosome. So that is a non-coding RNA. miRNA and siRNA are both involved in RNA interference, and they are non-coding RNAs. And they're used for RNA interference, which we will get into. RNA enzymes, which are called ribozymes, anything that has a ribozyme, Rosella talked about this on our Tuesday review, but if you weren't here, ribozymes are any enzyme that has RNA as its catalytic subunit. So while RNA enzymes have non-coding RNA in them, they are not only non-coding RNAs, because like a ribosome, a ribosome is a ribozyme, but it's also made up of different proteins that aren't RNA. So the correct answer here is 2, 3, 4, and 5. Those are your non-coding RNAs. Well, some of them, there's more. Like CRISPR RNA, LNR, or long non-coding RNA. So there's a few other ones, but these are the ones that we talk about in class. Any questions on that question? Okay, moving on. Here's our RNA interference pathways. We're gonna go more through this, but just a brief overview. Our question? We stopped at the 10th slide. Okay. Which slide is this? I'm sorry, there's like so much. 13. Oh, there's more. So we stopped at this one.
think so.
Okay.
I
Then
put a bunch
yes.
of question marks.
Oh, cool. Perfect. Okay. For this, we put question marks for this one, or we went through this one?
I did. I think she went through it really fast, but I didn't catch it.
Okay, we'll just start here then. Okay, so what would be the effect if region 4 were deleted in the trip leader sequence? And so when we're talking about section 4, we're talking about this section right here. Does anyone who did catch it in class want to speak up, or do we want to just put our answers in the chat again, or what do we want to do? You can just put your answers in the chat again if you want, and we can just go through it. Or if you don't want to put your answers in the chat, we can go through one by one, each of these. Any ideas?
Can we go one by one to also kind of state like
Yeah.
why that wouldn't
Yes.
be a reason?
I want to go, here's my idea, one by one. Everyone knows how to use your thumbs ups and thumbs downs, right? Can everyone figure out how to use the thumb up and thumb down? If you do know how to use it, can you give
I get
thumbs
it.
up? There we go. I got a few thumbs. There we go. Awesome. Okay. So if you think it's right, you're going to do a thumbs up. And if you think it's wrong, you're going to do a thumbs down. Okay. And I don't think anyone can see that on the recording, so you don't have to be embarrassed. If you're insecure about your answer, please give me anything. If you have no idea, just send a random emoji. So what would be the effect if region 4 were deleted in the trip operon sequence? So number 1, full length trip mRNA would be overproduced. Is this true? I got 1 thumbs up. Anyone else? I got 2, I got 3, 4. Okay, thumbs up. So we're all agreeing thumbs up. So yes, this would be true because what can't happen if we don't have sequence 4? Someone shouted out, come on, what can't happen if we don't have 4? Or type it. Attenuation, yes, attenuation can occur. So if we don't have sequence 4, attenuation can't occur, which means even if we have enough tryptophan, we're not attenuating, we're not stopping that transcription. And so full-length mRNA, trip mRNA would be overproduced. So then number 2 we know is incorrect. So we're gonna skip that because it's the opposite. 3, full-length trip mRNA would never be produced. Well, we already answered 1. If it's overproduced, that means it is produced. So we don't have to worry about number 3. This would increase transcription of the trip leader sequence. So this is the trip leader sequence, right? So what do we think about this? Yes or no? Or I don't know. I got a no. I got a thumbs up. I'm 50-50. I got another thumbs up. So this one actually is not true. So this would not increase transcription of the trip leader sequence because this is the leader sequence, right? And we transcribe the leader sequence not no matter what, but the transcription isn't affected by attenuation. The transcription of the entire mRNA or the transcription of the entire sequence is dependent on whether we attenuate, but the leader sequence itself, which is the sequence we're looking at here, like the sequence, is not affected by whether we have attenuation because it's going to be transcribed. Whether or not it continues transcription is what depends on the attenuation. Does that make sense? So we would not increase transcription of the leader sequence. It's going to be transcribed the same. Good. Someone still has their X up. I don't want to call you out, but you have to click it again for it to go away. Okay, I just want to make sure that you didn't have a question. Okay, number 5, this would increase translation of the leader sequence, or this would increase translation of the leader sequence. Is this true? Any ideas? I got one yes. Anyone else? Okay, so this one is also a tricky one, I guess. So yes, so this is actually true. No, yes. This is a good question. Is it going to transcribe to the end? Whether we attenuate or not. Did anyone catch this in class? Was this correct? We went through it. Did anyone write down whether 5 was correct? Because I have my guess, but I don't want to, you can put it in the chat if anyone has it. If not, I might come back to this and pull up the slides because I don't want to give incorrect information. My thought is whether we attenuate or not. I think if we attenuate, the ribosome is probably going to fall off, but it might continue translating. So once I'm going to come back to this and come back to number 5. If I forget, please remind me because it'll be in the class notes. Okay. This would increase translation of the TRP operon genes. Is this correct or incorrect? No one's playing my game anymore. I think that's an I don't know face, but I like that one. Thumbs up. Okay. Thumbs up. Check. Okay, awesome. Yes. So this would increase translation of the TRP operon genes because, like we said, if we don't have attenuation, then we will transcribe even when we're not supposed to. And if we're transcribing, then we're translating because it's a prokaryote. So we would have increased translation of the genes, which would be a problem because then we'd be wasting energy making tryptophan when we don't need to. Like I said, I'm going to come back to this question and just really want to make sure I don't give you guys the wrong answer. Do we have any questions on what I did confidently go over before we move on to the next one? Okay, we can come back. What would the effect if region 2 were deleted? What would be the effect if region 2 were deleted? And we're assuming that RNA polymerase pausing can still happen, but the 2,3 hairpin cannot form. So for one, so think about it for a second. So we delete region 2. So for number 1, full length TRP mRNA would be overproduced. True or false? I mean, let's start with if region 2 gets deleted, will this have an effect? Yes or no? Is it going to make a difference? Yes. If we can't hairpin 2 or 3, what is always going to happen? If 2 and 3 don't hairpin, what does hairpin? Three and 4. So if 2 and 3 don't hairpin, 3 and 4 always hairpin. So what is always going to happen if they're hairpinning? Attenuation. Attenuation is going to happen whether we're supposed to or not. Because if 2 and 3 can't hairpin, 3 and 4 are always going to hairpin. And if 3 and 4 are hairpinning, then we're always going to have attenuation. So if we have attenuation, even when we shouldn't, are we overproducing mRNA?
No.
No. What are we doing?
Underproducing. Or
are we underproducing or are we never producing?
Oh.
I guess underproducing, technically we are underproducing, but we are also never producing. I don't know if we count both of them, but yes, we are underproducing because we are never producing. Because if we attenuate every time, then we're not producing any mRNA. Does that make sense?
Yes.
Okay. I mean, you're not wrong. We are underproducing because we're producing less, but we're not producing any at all. So you wouldn't have a test question like that. Don't worry. This would increase transcription of the TRP leader sequence. This is the same concept as the last one, that this does not affect transcription of the trip leader sequence, because we're doing that. Number 5, I still need to look for. And then are we increasing the translation of trip operon genes? Yes, no, maybe so. I'm gonna have to pull my nails out if we don't start answering questions. Come on, people. Are we increasing translation? We're doing the opposite of last time, and last time we were increasing. So are we increasing?
No.
No, thank you. We are not increasing, we are decreasing. We're not translating because we're attenuating, okay? And the next one, what would be the effect of the trip codon if the trip codons were replaced by stop codons? So our trip codons here, what's gonna happen if we have stop codons instead? I mean, I think that this is pretty straightforward. Can we agree that if we replace trip codons with stop codons, we're probably gonna stop
Nothing's
doing
gonna happen.
Yeah, nothing's gonna happen. If we put stop codons, well, not necessarily, because stop codons just stop translation, not transcription. So we're not gonna have a pause. We're not gonna pause on the trip region. So this is a funky one. So we're not gonna pause on the trip region, which means I think we're always gonna make full length mRNA, right? Because if we don't pause, we attenuate. Yes? So we don't pause, we're gonna attenuate. So we're not gonna make anything. Does that make sense?
Mhm.
Everyone else good? Any questions about this one? I know I'm kind of going through them now, but I was tired of my game. It was not working out the way I wanted it to. Okay, so then we did non-coding RNAs, and now I'm just going to quickly run through the RNA interference pathways. So we have miRNA on this side, and we have siRNA on this side. As you can see, miRNA starts in the nucleus. siRNA comes exogenously, so it's outside the cell. So we start outside the nucleus. We run through on the inside, we have extra since we're translating it or transcribing it from our own DNA. We have to go through some DROSHA processing, go from pre with an I mRNA to pre with an E mRNA. There's a great explanation of this on Tuesday's recording, so I don't want to spend too much time. And then we use exportin, which we love, to get outside the nucleus. And then we kind of line up where we end up having dicer, and then the RISC and Argonaut complex come in and cut. We find our strands, and if we have an exact match, which usually happens in siRNA, we completely degrade the mRNA that we targeted and we chew it up, versus if we have not completely complementary match, we go to the P-body for either waiting, repression, or degradation. And that normally happens with miRNA. We can come back to it if we have further questions. That was just a very, very quick rundown. We're going to go into it more.
Yeah, I do have a quick question a question, but it has to do with the problem set. So I didn't know if you wanted me to wait until.
Yeah, we're going to wait till the end for problem set questions.
Okay.
So that's the quick rundown. And I just don't want to go too far into it because I have a good question about it and I don't want to spoil it. So true or false, miRNAs are encoded for within the genome, typically doesn't exactly base pair with the mRNA, and so could bind to multiple different RNAs. True or false? True, thumbs up, false, thumbs down. Anything? I got a no. Got a false. Anyone else have any thoughts? Any I don't knows? We got another no. We got a no. Okay, so this is a tricky one. So let's break it down. So there's 3 parts to this. Are miRNAs encoded for within the genome? Yes, I can't wait for thumbs up. Yes. Do they typically not match exactly? Yes. But can they bind to multiple different RNAs? Not so much. So it's still specific where we have to have, it's kind of like consensus sequence, which we talked about this week, where they don't exactly base pair, but they're still pretty darn close, because if they could bind to a bunch of RNAs, we'd be chewing up a bunch of stuff or sending a bunch of stuff to the P-body that we don't mean to. So this is partially correct, but the conclusion is not correct. So they do come, but because miRNAs are encoded for within the genome, and they typically don't base pair, but they are still specific to the mRNAs that they target. Does that make sense? Okay, last one. When there is an exact match between the guide RNA and the target mRNA, what is most likely to occur? People can either shout it out or put it in the chat. Any ideas? Okay, we got a few. So when there is an exact match, we degrade. So if you remember, siRNA is on this one. So when we have an exact match, we chew it up. When we don't have an exact match, we go to the P-body. So in this case, which is most likely to occur, degradation of mRNA. Sequestration of mRNA into the P-body is when we have not exact base pairing, which would be post-transcriptional silencing, or that would be translational silencing. Degrading the mRNA, I believe, is post-translational silencing. Correct me if I'm wrong. So I think that the answer is 3 and 4, or 1 and 3. I'm sorry, numbers. Does that make sense?
Yes.
Okay. So that's our clicker questions. We can come back to it. Don't let me forget to come back to 5. Actually, I'm going to do that right now. So I'm going to stop sharing this real quick. I'm going to pull up the class notes, because I really want to make sure that I know what I'm talking about. I don't want to lead anyone off. They're not up yet for today. Okay. I will send a follow-up email, because I don't want to give anyone any false information or anything. So I will follow up with that, okay? But on to topic 4, review the slides I made today. So now we're going to get into some past problem set questions that are similar to what we're going to see on exams. So first, transcription factors. I hope everyone enjoys my kidney bean picture. I put kidney beans because I think Sigma 70 looks like a kidney bean. I thought it was funny. So that's me explaining my joke. I hope you enjoy it as much as I do. So first question. I'm pretty proud of this, so I hope everyone enjoys it because I made this. So which are general transcription factors, regulatory transcription factors, neither or both? So I made a little Venn diagram and I have it filled in on the next page, but I want to start with, these are your 5 options. So sigma factors in prokaryotes, basal transcription factors in eukaryotes, RNA polymerase, triple repressor, and tryptophan. So either calling out or in chat, which again, you can privately message me, And if you have no idea, please please send that. I am going to wait until I have at least 4 or 5 people respond. Just write down which ones you think are general transcription factors, regulatory, both, or neither. I'll give everyone a minute. But yes, please enter that in the chat and then we will see what everyone's thinking. Oh no, sorry. I hope no one saw my spoiler. I'm assuming everyone's typing. If people are not typing, please send me something, an emoji. I don't want to play, no idea, I hate it here, whatever you want. If you just aren't typing out, please send me something. Okay. So I got 1 message, 1.5. Done. Okay. Okay, I got a few. Okay, well, I'm going to move on to the next page. If you want me to stop and wait still, speak now or forever hold your peace. Okay, so the correct answer is as shown below. So sorry, I have to keep moving people's faces so that I can see my own screen. So we'll start with general transcription factors. Are the transcription factors necessary for us to actually do transcription? So in prokaryotes, the sigma factor is necessary to bring in RNA polymerase, and that's our sigma 7b is the one that we're discussing in this class, and it looks like a cute little kidney bean. And then basal transcription factors are required in eukaryotes, and those kind of come in and make a complex to bring in RNA polymerase so that it can bind. So those are our general transcription factors. The TRIP or regulatory transcription factors are anything that activate, enhance, or repress transcription. So the TRIP repressor is a regulatory transcription factor because when it's bound, it stops transcription, and when it's unbound, transcription can occur. So that's regulatory. RNA polymerase is not a transcription factor. Transcription factors bring in the RNA polymerase, but RNA polymerase itself is not a transcription factor. And then tryptophan, it's a co-repressor, but it itself is also not a transcription factor. It is just an amino acid. Does that make sense to everyone? Does anyone have any questions on this? And there's no boths. Surprise. Any questions? Anything you want me to go over? Are we ready to go on to the next one? Okay, I don't see any questions, but I can always come back. Number 2, the TRIP operon. Here's my humor. Our little repressor's in the way. He's very unhappy. And there's our promoter and operator regions. Okay, sorry, I'll stop laughing at my own jokes that I found, but this one's a long one to read. So assuming that transcription is largely suppressed at high amounts of tryptophan, that in the presence of medium concentrations of tryptophan, the transcripts of the TRIP operon synthesized are primarily of the short or attenuated variety. And in situations where there is no tryptophan, transcription occurs and is not attenuated. Determine how regulation of this operon would change if the TRIP codons in the leader sequence were mutated to alanine codons, an amino acid that is always present in the cell at abundant levels. I should have included a picture here. So I'll show you a picture as to what I'm talking about here. And by that, I mean Laura, because I did not write this question. I stole it. So we are referring to, in the leader sequence right here, as opposed to having trip codons, we have alanine, and alanine is always present in the cell. So we're looking at what's going to happen at each of these levels. Okay, so I already have the answer up there. So at high levels of tryptophan, is it going to look different? So we switch these codons to alanine. And if we remember, at those trip codons, that's where we have our pause, right? The ribosome waits for tryptophan to come in. So if we think about it, if they're mutated to alanine, then it's always present. So is the ribosome ever going to pause and wait there?
Really quickly, what did you say the ribosome pauses for? Like, what's it waiting for?
It's
Just
trip codon. So if you remember, it waits for the tryptophan to come in, right? Because if there is enough tryptophan, it comes in, it keeps going, and that's why attenuation occurs, right? And then if we don't have tryptophan, it pauses, and that allows the 2 and 3 to hairpin. So in the case of alanine, so this is still the trip operon. We're still making tryptophan, but now we're waiting for alanine. But alanine is always in the cell. It's always present. So are we going to pause on that region? If alanine is always present, are we going to pause? It's a 50-50 shot.
I'd go with no.
No, we're never going to pause. And if we're not pausing, then what? Do we attenuate or not attenuate? What hairpins if we're not pausing?
1 and 2. No. Yes.
Mhm.
1 and 2.
1 and 2. So then if 1 and 2 hairpin,
3 and 4 have the hairpin.
3 and 4 hairpin. And so we get, yes, attenuation. So
Okay.
we have the alanine. And so in this case, we just talked through it. Attenuation is always occurring. So at high levels of tryptophan, is that going to look different in the long run? Because at high levels, we're not making tryptophan, right? When we attenuate, are we making tryptophan?
No.
No. So at high levels of tryptophan, we're not going to look any different because we're not making any. At medium levels, we're going to look similar because remember the trip operon, we are mostly attenuating, sometimes not. And so medium is not going to be as affected, but at low levels, are we going to see a difference?
Yes.
Absolutely, because at low levels, we want to be making tryptophan, but since alanine is always available, the ribosome is never going to pause. We're always going to attenuate, and we're not going to have any translation of these proteins necessary to make tryptophan. So a summary of that is, at high levels, we have no change, little transcription in both cases. Medium levels, attenuation will occur in both strains. And attenuation happens most of the time in the alanine strand, which we already knew. And then at low levels, attenuation occurs in alanine, the alanine strand, when it shouldn't occur. So no tryptophan is made, and that's bad for the cell. Does this concept make sense to people?
The concept makes sense to me, but then I get confused when we're switching like to alanine or another amino acid.
So my advice on how to approach a question is like this is, okay, we switch to alanine and just focus very specifically on what that part did. So we switched to alanine, and we know if we switch to alanine where the tryptophans were, then an alanine is always present, then we know that it can always come in, the ribosome doesn't pause. And then take that piece of information and figure out how it works in the grand scheme of things. So I wouldn't approach it looking at every level, I would build up. So start from the smallest thing you can. Okay, we switched alanine for tryptophan. How does it normally work? And how is this change going to affect that system? And that's why we do these review sessions now that are more similar to actual questions we're going to see, because we can have more practice with this. Does that help at all? Just trying to, it takes practice.
I think so, but then I get, because I understand what's happening with just tryptophan, but then I get confused, or I don't know if I just get overwhelmed or confused or whatnot when we add in another.
I would just keep practicing questions. So practice these questions, redo your problem set questions, practice until you know it like the back of your hand. That's pretty much what you got to do. So we're trying to give you as many questions as possible in different scenarios. So do your clicker questions, do these questions, do your problem set questions. And it'll start to be easier, but it is very hard. I completely understand. That's why this week is very hard, and I'm happy everyone's here or everyone that is here, because this is one of the harder weeks and we didn't have a lot of class time. So, and we can come back and practice this more if you want at the end, if we have time.
Okay.
So I'm going to move on to RNA interference. HBV is the hepatitis B vaccine, just in case anyone was wondering, and that's my meme for this slide. So we're doing it again. So we're comparing and contrasting siRNA and miRNA RNA interference. So in the chat, give me some similarities or differences, call them out. Differences are going to be easier because there's only really 2 or 3 major differences, and then everything else is pretty similar. So shout them out. If no one participates, then we're leaving it blank. As I'm going to fill it out with everyone. I'm prepared. So, oh no, sorry. Give me things and I'll edit this and I'll send it out to class. And if not, I'm not typing anything in. So it's on you. And you can direct message me, and then if you're wrong, I won't. They are both involved with interference. Yes, this is true. So they're both involved in RNA interference. One starts in the nucleus and the other starts in the cytosol. Which one starts in the nucleus? Anyone? siRNA, where does it start? Nucleus or cytosol? Yeah, so miRNA is in the nucleus, siRNA is in the cytosol, which means it is, which also means it's exogenous, which means that it comes from outside the cell versus this starts in the nucleus. And it's endogenous, which means that it is coded for in our genome. Different differences or similarities. What are some proteins involved in both processes? What cuts things? What trims the mRNAs, or the interfering RNAs? They both use dicer. Perfect. Anyone remember what dicer does? If I go back to this, it cleaves specifically. I'll show the picture. So dicer we find here at the top, and dicer, it essentially processes the double-stranded RNA. I can't get back to my Google slide. Sorry. Okay. So dicer cleaves and processes si/miRNA. Okay, what else? What processes miRNA that siRNA doesn't have? What's it called? Also starts with the D. DROSHA, yes. So we have DROSHA processing in the nucleus. Let's talk about pairing siRNA. Is it normally in a complement exact base pairing? or non-exact base pairing for siRNA first. Anyone? Am I backwards? Because I really truly believe I've been saying siRNA is exact base pairing. And everyone is saying the other. Am I going crazy? I might be. I believe siRNA is exact base pairing, which then leads to mRNA degradation versus mRNA, which is non-exact base pairing. That leads to mRNA sequestration to the body. Does anyone have a strong objection to that? Am I losing my mind? I might be. I know it was a 50-50 shot and it might have just been a guess, but I believe siRNA, because siRNA is usually viral, so it exactly base pairs and degrades because we don't want the virus, versus miRNA, which is endogenous, so it's in our genome. So sometimes sequestration is good. Okay, so yes, that's a lot of the main differences between them. So do we have anything else that both of them do? Will it be helpful if I go back to this picture? What else is involved in both of them?
Ribosomes to like make them?
Actually, no, because the ribosome only makes, well, this is mRNA, or these are RNAs, so they actually haven't been translated. Ribosomes are translated. So these are our non-coding. That's a good guess though. But we do have RISC, which RISC is not, I just totally lost the word. RISC is not a ribosome, but RISC is involved. And we also have Argonaute, which is the, what actually cleaves. So those are in both. The RISC cleaves siRNA or unwinds the miRNA, which says here. And so the miRNA ends up single-stranded to go bind. siRNA is a little different process, but they're essentially the same when it comes to RISC and AGO2 or Argonaute. I'm sorry, I kind of just went off on a tangent there that didn't even make sense. Oh no, did I stop sharing? Oh my gosh, this is all just falling apart. Glad this is gonna be on YouTube forever. Okay, so this is a pretty good list. Does anyone else have anything they're very passionate about putting on this list? Yes, no, maybe so. This is pretty good for comparing and contrasting. If you're asked to compare and contrast, this is a pretty solid list right here. Are we good with that? Because we have the mainly what happens, and obviously in here we have our Durocher processing. We make it pre-mRNA to then pre with an E, miRNA, and then we exit. And then we have our dicer processing, RISC and Argonaute, and then the biggest other thing is the base pairing, and usually siRNA is degradation and miRNA is sequestration, which can end up in that could end up being degradation, but it also doesn't necessarily have to be. And yeah, that is a pretty good list, and I think covers most of the really important points. So if you understand this, that is good. Do we have any questions on it? Okay. So this is the end of the presentation I have. Here's my email as always, which you can find everywhere. And I also send out emails like all the time. So feel free to email me with any questions. Does anyone have any questions or anything they want to go back to and go more in depth with before I stop the recording and we do prompt set questions? Are we all in it for the prompt set questions? I dig it. You got through 50 minutes of me lecturing, so I respect it. Okay, so I'm going to stop the recording. So everyone on YouTube, feel free to email me if you have any questions. And